Okay, very good. So I was just saying we started reviewing the magnetic materials, and we saw that there are two types of magnetic materials. Diamagnetic, where the magnetization produced, which is essentially a response of the material to the applied external magnetic field, is in a direction opposite to the applied field. That's called diamagnetic. And then paramagnetic, obviously, which is parallel. Then you can make a perfect diamagnet, which is a superconductor in this case. For a perfect dielectric, you don't need a superconductor. A normal conducting material that we find every day around us is sufficient. So that's one big difference. And then there was another class of paramagnetic materials, I believe, that we looked at. Yeah, para is just parallel, and it is not necessarily exactly this. The response would depend on what sort of material we're talking about, right? And so most of what you have learned for dielectric materials and also for magnetic materials, the detailed calculations are not really part of the domain of electromagnetic theory that we're going to study. The detailed microscopic calculations always come from quantum mechanics, right? And it's the domain of the so-called solid state physics or condensed matter physics, which we're not going to go into the details of, though we will point out some formal definitions. And after that, then you just deal with kind of the materials that you're talking about. Okay, so those are the three types of materials that we look at: paramagnetic, diamagnetic, and we treat the superconductors separately because they they essentially eliminate the magnetic field, external magnetic field, completely inside of them. So the magnetic field is zero inside, which is called a Meissner effect, if you have seen that, which allows you magnetic levitation and those kinds of cool things. That itself is a very interesting area of study if you want to go deeper in that. So let's now take a look at the formalism. We started looking at some basic things, right? So we will set up the theory, and then we will take a look at a few examples, right? And so I have, just to help get back on track, this is something we already discussed, and it turns out we don't, there is another difference between the electric case versus the magnetic case. In the electric case, there is no separate contribution of spin and orbital. We don't worry about that. There's just no such a thing, right? Because it's just charge separation is what matters there. When it comes to magnetization, because the origin is from current, there are two terms that are important, right? And so there is a spin magnetization and orbital magnetization. And out of that, spin may look complicated, right? But it turns out spin is actually fairly easy to deal with. Orbital gets complicated, and so we will take a look at some of those details here. So the spin magnetization is just basically, think of your material as a collection of spins that are situated at positions Rk, and so you just do a sum over a spin magnetic moment of each spin multiplied by its current, corresponding delta function, which just gives you where it's located at, right? So that's all there is to it. Very simple, and it almost always is determined using first principles quantum mechanics, right? So you figure out the positions Rk where your spins are situated at, and then you go into the details of determining this, right? So formally looks simple, but in practice, each material is different, and that's where a lot of theory and experimental investigations kind of tell you where you are. Determination of the orbital magnetization, not so easy. You can only, using quantum mechanics again, you can only determine the current density and translating that into the orbital magnetic moment. We will see how that process works, but it turns out it's not unique, right? And so we're going to kind of dig deeper into that. But first, before we do that, right, so let's actually take a look at the spin magnetization current density in detail, right? So this is the spin magnetization, but the origin of magnetic field is always some sort of current, and magnetization is a material produced magnetic field. And so there needs to be some current density that is generating that, so which we can determine, right? So let's take a look at spin magnetization current density. And you can determine that basically just as Js of R. And once you know Ms of R, which is the spin magnetic current and spin magnetization, you have to just take a curl of it, right? So that it's as simple as that. Take its curl, you're going to get that, right? And so what we're going to do is we're going to assume that you have a region here of space where you have no spins, Z, right? So let's say that's a Z axis. We have no spins there. I'm going to actually change the color of this so we can quickly see what's happening. Okay. And there are the spins in Z less than 0 region. Right, so spins are all situated there. In that case, you can actually dig deeper into understanding the volume current density and the surface current density. There are going to be both contributions coming. Whenever you have a finite volume, there's going to be surface contributions from the surface of that finite volume, right? Okay, and so you will have to look at the magnetization multiplied by theta of minus Z. Right, so you know the theta function that you studied in the first chapter, where a normal theta function, where theta of Z is a step function. In the positive Z region, it has a value 1, and then it is constant after that. In the negative Z region, it is 0. If you want to switch that, all you have to do is substitute minus Z, right? So that's all there is to it. And so then the current density we are going to, so this is what matters. Your magnetization is confined to the Z less than 0 region. And so that means when you take the curl, the curl has to be of this product quantity, right? So you just use the chain rule to determine the magnetization current density. And because there are 2 terms, there would be naturally 2 terms. First one is simple. We just do the curl of the, curl of the magnetization in the region. And so this contribution is the volume current, because theta of minus Z just tells you that you're within that region. But the other term where you take the derivative of the theta function, anybody knows what's the derivative of the theta function? Right, the derivative is 0 in the Z less than 0 region, derivative is 0 in Z greater than region, but at Z equal to 0, there is a big bump, right? So it is basically like a delta function. And so this is what you get when you differentiate theta of minus z, you get z hat delta of z, and that is now going to be a surface contribution because it is only prominent at z equal to 0, which is the surface of that volume that we are looking at. Okay, so that current density can be split into two parts, essentially, surface current at z equal to 0, essentially, right? And so you can calculate or you can determine the surface current as a function of, let's say, xy, because the boundary plane in this case is going to be a xy plane. You just do a z integral of the js, and because it has only the delta of z, only z equal to 0 term contributes. So ms of xy times c hat, that's going to be your current density, or in general, you can write it as on some surface coordinate or surface position rs, the surface current density is going to be ms rs crossed with the normal vector. So this is in general, and this is a special case as in the figure, right? Why the first one is special case? Because we're assuming that the normal vector is always along the z direction, which may not be the case. If your boundary is not flat and smooth, let's say it is a surface that has different it's not a flat surface, it has say valleys and troughs and crests and so on, or some arbitrary structure, then that arbitrary structure can be pulled out by the normal vector at each position. The normal vector at each position could be different, and so you could still calculate the surface current density, the spin magnetization surface density at that position. Okay, so that's how you would deal with the spin magnetization part. Any questions anybody had so far? Okay, so you could think of visually as two terms for a finite size material, right? We don't have infinite materials where volume would be sufficient, right? So that's not the idea here. Okay, so let's now take a look at the orbital current densities. So orbital magnetization. Anybody has any questions so far? Does the theory sort of make sense? Okay, so the same idea again, you could say J orbital of R would be curl of the orbital magnetization that you somehow calculated, let's say from the first principles, right? Okay, so R is so this is now the volume current density. We're going to write down the surface current density against. I'm not going to go through the calculation. You get the idea. It is essentially going to be the same logic, so I can directly write down R is element of the surface that is confining that volume, and the magnetization is equal to 0 if R is not element of the volume of interest where the material is sitting, right? So that's all there is to it. Very simple. Okay, but the challenge is, so what's the challenge? Let's take a look at the challenge. The challenge is let's not separate that, right? So the challenge here if we add some, a term that's a gradient of some scalar field, lambda, let's say, to MO of R, it does not change the current density. So that's a problem, right? That means the MO is not unique, or rather M of R, due to the orbital magnetization. I think I should just straightforward say MO of R is not unique. Okay. Spin one, things are simple. You just count the spins and that's it. You get that. Here, it's a little tricky because J0, JO rather, is physical, meaning the electrons in the material are going to move around and that's going to cause this. So there's a physical origin behind this, right? And in some sense, what we have done here is I gave you J0R as a curl of MO, right? So once you know J0R, you need to invert. So the next step is invert JO equal to curl of MO to get JO, not to get, let's see, to get MO, right? To get the total magnetization. So you are going to get orbital magnetization only by looking at the current densities that you calculate from the first principles. But this is not unique, right? As you can say, MO plus any gradient of a scalar function lambda R would give the same current density. Same orbital current density. And so this is similar to the gauge freedom that we talked about for the scalar potential, also exists for the vector potential, which simplifies the mathematics for us in the case of the vector potential. But here it adds some complications. This means that a quantity that is not fixed, that is not unique, cannot be physical. That means MO by itself is not physical. You need to be able to fix that gauge freedom somehow.
That means unique?
Is not unique. And if it's not unique, then it is not physical.
Could you explain how it's not unique?
Right. So for example, the electric potential is not physical. What's more important is the potential difference, right? So you always talk about potential difference. That's all that. So you need to, that quantity by itself is not physical. You have to come up with some modification of it slightly that would be more physical. That means no observable quantity depends on MO alone. Okay, and then there is a prescription that Lawrence provided to fix some of this, not completely idea. And as a result, it also, you can make the same conclusion about MR, right? Because MO is part of MR. That's where the challenge comes from. So this is all a bit complicated. Okay, so this is just to tell you that there are some issues here that may be still unresolved, right? I mean, they may never get resolved. That's the trouble. Let's take a look at the Lorentz averaging procedure, and then we will put the theory all together, and then we will look at a couple of examples. Right? So let's first take a look at the Lorentz averaging procedure, because the origin of the magnetization is microscopic, but in electrostatics we deal with macroscopic, and so you need a process to go from one to the other, and you already saw the implications of that, not doing that correctly in the electrostatic case. Here, there we saw that there is a modern theory that sort of improves upon the Lorentz model issues. In the magnetic case, there is no way out, right? So what we do is, again, the same procedure, averaging procedure, M of R, the total magnetization is a volume integral of essentially the microscopic current density on that, in that volume, and then you do S crossed with Jm. That's going to give you the and you can see this is omega dependent. That's the dipole moment, magnetic dipole moment. Because we define the magnetic dipole moment M of R is the volume integral of capital M of R, volume integral of the magnetization. So that's how that just works. Okay. So this omega dependent, we saw in the case of electrostatics, there was a way to remove that by adding time averaging. You can't do that here. It turns out it's problematic. So you can't do, there's just no way around it. I'm not going to go into the detail. You can take a look at the discussion in 13.2.5. So here's a reading assignment for you. Okay, and these reading assignments are going to be crucial because you remember your final exam is going to be oral and it's going to be conceptual. And so make sure you take all those reading assignments seriously. Okay, so that's the challenges that still exist with the magnetized material. Let's put the theory together and then we will take a look at the examples. Right, so we of course talked about the total magnetization in the beginning. M of R is the spin contribution plus the orbital contribution, okay, where you can then calculate the Jm of R, which is the magnetization current density. Once you know the magnetization, which you can measure, by looking at how the material responds to the magnetic field. And so you get the curl would give you the magnetic volume current density, and on the surface, because you always have boundaries to the surface, you will have contributions like this. Okay, so that's that. You kind of put the two things together, and this is what you get. The magnetic moment, I think I made a mistake here, did I? No, I think that's fine. So the magnetic moment is defined as half of the volume integral d cube r crossed with the magnetic current density, the volume contribution, and then there would be a surface contribution from the surface current density also. That would be again R crossed with the surface current density or surface magnetization Km. Okay, that's that. Let's put that in a box. Okay. So you can do some manipulations of this and simplify it, and eventually you could prove that all of this leads to M equal to the volume integral of big M. Okay, that's all there is to it. Okay, and what are the steps that are needed? You need to do the Cartesian representation and use epsilon ijk, the Levi-Civita symbol, to figure those components out, and then you will see that that's what it amounts to essentially. Okay, so you can go through that. The mathematics is straightforward. Details in section 13.2.4. Again, you can kind of see that I'm not going in the order in which the book does it. The logical order for me is, for detailing the description of what's going on is how I'm doing it here. Okay, so that's that. We are more or less close to ending, coming to the end of the theory discussion. Let's now write down the field produced by the magnetized matter. Once you have that, then that does it, because that's our goal here in E&M. Somebody gives us a charge distribution and the current distribution, and then you have materials present and what is the magnetic field that I'm going to get in that situation. Okay, so now we're going to take a look at the field produced by magnetized matter. And so for that, if you can calculate the magnetic vector potential, then you are home free. So let's write down how the magnetic vector potential is going to look like when you know the magnetization, right? So mu0/4 pi volume d cube r prime curl of volume integral of the curl of M evaluated at r prime, r minus r prime, plus mu0/4 pi, the surface integral of the over r minus r prime. Okay, so where did I get this? It's actually very simple. Remember, that's your volume current density and that's your surface current density. So all you have to do is just do a integral of the volume current density, volume integral of the volume current density divided by the Coulomb distance term. That gives you the component to the vector potential corresponding to the magnetization, and then the surface current density integral over the surface gives you that. So as simple as that, nothing complicated. And then of course, once you have this, you can calculate the take the curl of this expression, and then you can determine the magnetic field. So I'm just going to quickly write that down for you. Oh, and that is going to be mu0/4 pi volume integral d cube r prime. And then all you have to do is take the curl of the previous expression with some simplifications, of course, and as an end result, this is what you get, r minus r prime in parentheses divided by What term do you expect at the bottom there? Anybody? Remember, the curl is taken with respect to the r coordinate. So you really have to take the curl of only 1 over r minus r prime. When you do that, you get r minus r prime vector divided by r minus r prime magnitude cube, right? That's just the Coulomb term. That's what you get. Or in this case, it's a Biot-Savart term because that's corresponding to the magnetic situation. So inverse square law essentially is what I'm trying to say. Same thing here, m of r prime crossed with n prime. You don't care about these. The derivative doesn't apply to that. So you only have to apply it to r minus r prime term because it's a derivative with respect to r. And then that gives you r minus r prime over magnitude of r minus r prime cube, right? So that's all there is to it. And so you get the magnetization, vector potential, and the BM every point in space. And then you need to evaluate these integrals essentially to calculate this. Right now, of course, this is prohibitive. It's not always possible to do it this way. And in simple cases, we can do that. The other approach to this is the boundary value problems, which is what we will take a look at on Thursday. Right? So Thursday would be sort of conclusion of the ideas and how do we overcome the mathematical difficulties of evaluating these Coulomb integrals, right? This is standard, this is correct, everything is there, but the mathematical inconvenience of not being able to calculate something is a problem, right? So you want to be able to deal with those. And so we deal with those with the help of representing, again, going back really to the vector potential in the magnetic case, or the scalar potential. There is a scalar magnetic potential as well, and the scalar electric potentials, and then writing down the differential equations for those and solving those differential equations with the help of the boundary conditions that you are familiar with, right? So it's the presence of boundary conditions and having limited volumes that you need to deal with is what complicates doing these integrals. And the way you deal with that is through the solution of Laplace's and Poisson's equations, which of course the solutions are a complete set of orthogonal functions. That means a general solution can be written down as a superposition of these eigenstates of the differential equation, if you will. But those eigenstates, those are just general solutions with undetermined coefficients. To determine the coefficients, that's where the real physics comes in. You apply the boundary conditions and then simplify the mathematics, right? So that is something that we will take a look at in the next class. That was just my 5-line exposition of how the process sort of works. Let's now take a look at a simple calculation of the magnetic field due to a magnetized material. And again, we're going to take a look at a simple, very, very simple example where you have, and this comes from the book 13.1. I will have to draw a little picture here. So imagine you have a slab of material and it's infinite in extent, and you have the current, and we are taking a cut of that slab, right? So you have a current that's coming out here, current that's going in, the current that's coming out, current that's going in, and so on, right? So you can and so this is not the real current. This is just the diagrammatic representation of how to think about the magnetization that you're getting, right? Okay, so I haven't shown the magnetization yet. This is not a correct order, actually, as it turns out, of drawing this, right? So these are magnetization currents. And in this case, they would be surface currents. Remember, we talked about the surface current Ks. That's what these two things are. The magnetization itself is given to be like this. I'm going to use a different color for that. So magnetization is coming at an angle. And it's uniform, meaning it's parallel in, the lines that I'm drawing. Assume they're parallel, the drawing program here may not do that, and they are equidistant from each other, even if it doesn't appear that way. Okay, and that's the magnetization M. So the magnetization is given to you. You have a little slab of material that has magnetization that's uniform, and at an angle, let's say theta, with respect to the vertical. The angle is theta with respect to the vertical. Let's take the distance between the width of the slab to be d, and let's take our coordinate system to be x here horizontal and z vertical. Okay. And then the currents are coming and going in the y direction, if you will. Okay, everybody with me? So magnetization currents, that's just our sort of mnemonic or a aid for us to imagine what's going on. Right? The magnetization is the only thing that's given to us, where we can convert that by taking a curl into a magnetization current. Everybody with me so far? Okay. Now you could see that that current is only a surface current, right? So I'm going to now write here is only a surface contribution. Why is that? Can anybody tell me why do we only have a surface magnetization current, not the volume magnetization current? Any thoughts anybody has?
Because of infinite slab.
No thoughts?
Due to
I cannot hear you.
Can you hear me, Dr. Kapale?
Because the magnetization.
Can you guys hear me okay?
Yeah, we can hear you. Can you hear me?
Okay, so I'm having issues. So give me just a second here. Okay, go ahead, Anup, say what you were saying.
Yeah, maybe due to the skinning effect.
Steering effect, what is that?
I mean, the current usually moves at the surface of the wire. So maybe that's
right? If you have a thick wire, remember your elementary electricity discussions. The resistance of the wire depends on its thickness. That means the current, uses both the surface and the volume of the material. Why would, where does the current come from? Electrons, right? So why would electrons only be confined to the surface? Why would they not move through the volume of the conductor, right? So that doesn't sound physical, right? Anybody else?
I think it's related to the fact that the magnetization current within the object is uniform.
Right. Okay, very good. So remember, curl of M, if M is uniform in a certain direction, right, then the curl of it is going to be zero, right? Curl of, a set of parallel lines is zero. And so that's why you don't have any volume current density. You only have the surface current density, which does not come from the derivative of the magnetization. It comes from the fact that you have a boundary, right? There's no magnetization above the top end of the slab and below the bottom end of the slab. And so that gives you this delta function, which then goes into the surface currents. Okay, so that's.
Yeah, Dr. Kapale, we cannot hear you.
How about now? Can you hear me now?
Yes.
Yes.
Okay. All right. So we'll just leave it that way. So we understand why there is no volume current density, only the surface. If we know that so now if there is only the surface current density, we can determine it, right? So let's do that. We're going to determine it. So whenever you are solving a problem, you need to understand, really what's going on. Before that, there is no point in even attempting. So once you get the hang of what's happening, once the physics is clear, mathematics almost always is straightforward, and you can always take help from something for figuring the mathematics out, right? So if there is only now a surface current density which we can calculate, it's the uniform magnetic current time or magnetization times or the cross product with the normal vector, right? So m is this way, n is that way, right? So the angle, the magnitude of k is going to involve the angle between the two is sine, is theta. So you're just going to get m sine theta, right? Everybody with me? Just the cross product sine theta, and that's all there is to it. Really, we have determined that. And once you have this, then you can calculate the magnetic field, which I'm just going to write down. The magnetic field produced by the magnetization is going to be half mu 0 km in the direction x hat, right? Because m is this way. If you take the cross product of m with n, which is in the z direction, the k is coming out like this. Let's see, why is it in the m crossed with n is in the z direction, m is in some zx plane, so it should actually be along y. So I think there is if you look at the current density that we have drawn, the magnetization current density, that tells you it's like curling the fingers around the slab, and so the magnetic field has to be along the x direction. So I'm probably not doing something correct. Now k itself doesn't give you, k is going to be along the y direction, and then you need to take a essentially curl of k to get the magnetic field, and so that's there is another cross product involved, and eventually then you get the direction to be x, right? So that's how that magnetic field turns out to be. And so this is going to be magnetic field due to a sheet of current. Okay. And so the top set of currents give you magnetic field in the x direction, which is half the magnitude, and the bottom set of currents where the current is going underneath the slab and into the plane of the writing surface here will give you another half a contribution. So those two things add up, and so therefore the total magnetic field. So This is due to the sheet of current, due to a single sheet of current, right? And here for a slab, you have two sheets of current, one that's coming out, another one that's going in, but their contributions is always in the same direction because of the directionality of the cross product. And so adding the two, right? So you need to add the contributions from two sheets of current. The magnetic field would be mu0 m. So K is just m sine theta in the x direction, and that's going to be inside the slab. Outside, no contribution because there is nothing to contribute. The current density is 0 outside, right? And so that's not going to do that. Make sense? Everybody with me? Okay. And okay, so we're going to now, so conceptually what you can do is think about so I'm just going to make a couple of comments here and then we will do one more example. And so conceptually, magnetic matter can be thought of as a collection of point magnetic dipoles. Right? Spin, you can certainly think of that as a dipole. You can do the same thing with the orbital contributions. And so then you can, that allows you to determine the magnetic field due to some arbitrary material where you may not have uniform magnetization like we saw in this example, right? And so if you can calculate the magnetic moment of that material, the overall magnetic moment, which is, remember, it's a volume integral. If you are far away from that material, all of the magnetization in that material can be volume integral to give you the magnetic dipole moment of the total material, and then you can determine the magnetic field at a point that's far away, right? So there you will get the the contribution from the position of the dipole minus the gradient of, this comes of course because you are taking the curl of m as the to get the magnetic field, and so curl is going to give you this term r minus r prime cubed. Okay, and that's how you get the magnetic field at points far away from, so r is pretty much larger than r prime. Okay, so let's now take a look at one other conceptually important idea, which is what we saw in the case of electric situations, right? Once you put a dielectric material in the electric field, you get you get a volume charge density. There are some redistribution of charges inside, plus you get a surface charge density. Can you do the same thing for the case of for the case of the magnetic materials, and it turns out you can. And so what we are going to do is I'm going to just give you the let's see, I think let's not go into the details of the mathematics there, which would take up quite a bit of time. I would rather do an example. But the idea is similar to what we saw. You can think of, so let's just make a simple comment. Just as an analogy with the electric case, you can come up with fictitious magnetic charge, both volume and surface. Now you can see only situation where this would make sense is when you are using the magnetic scalar potential. Because if the physical problem allows the magnetic scalar potential to be used, then there is a direct parallel between the electrostatic case and the magnetostatic case. And in that case, then you can think about these fictitious charges. Right? If the problem cannot be explained with the help of the magnetic scalar potential, and you have to use the magnetic vector potential, then there is no parallel. Then the concept of fictitious magnetic charge is not very useful. Okay, so we might make sure you understand the domain where this applies. And so then here is the volume charge density that is corresponding to the determination of psi m. You can determine psi m as a volume integral of rho star of r, where the volume charge density is just the divergence of m, and the surface charge density is m at the surface, of course, dotted with the normal vector at each point on that surface. Okay, so this is just a mathematical analogy, if you will, between this between the magnetic terms and the corresponding electric terms. Now, can somebody tell me when can you use? So I'm going to ask you a question just as a digression before we start looking at the problem. When can we use magnetic scalar potential? And what are the conditions that allow us to use psi versus A? So we want to use psi, not A, but only in certain conditions. What are those conditions? Does anybody remember? Any thoughts anybody has? Nobody has any thoughts on it? So that's a question that might be on the test. So you might want to think about that. And not for everybody, right? Because the test is going to be unique for each one of you. It's not going to be the same for everyone. So that's the thing with the oral test, right? I will just come up with something to ask you, which may not have been asked to, the other students may not get the same thing.
Can I attempt the question?
Yes, go ahead, Malik.
What if I think we use it when we have symmetry.
Symmetry, what sort of symmetry?
I'm thinking it has, I'm not sure of the answer, but I'm thinking it has something to do with invariance of the theory.
Okay. So yeah, you do need to think about the answer. That's not quite correct. The answer actually is very, very simple.
Okay.
Okay, so think about this, right? So this is, just wanted to give you a flavor of the kind of conceptual questions you may get asked, and then you have to go deeper into what's happening. Okay, so only in that situation, when you are in that special case where psi is a good enough description of the magnetic phenomena, provided that condition is satisfied, then you can just bring in the mathematically convenient sort of concept of fictitious magnetic charge, right? It has nothing to do with magnetic monopole existence and so on, right? So that's not what we're talking about. We're just saying you have a surface currents versus volume currents, right? That's all there is to it. Okay, so now let's take a look at another example, which is similar to the example that we looked at in the dielectric case. We looked at a uniformly polarized sphere. Let's take a look at uniformly magnetized sphere. So you will then see the difference and the similarities between the two. So this is example. This is actually so-called application in the book. And we are going to look at a uniformly magnetized sphere. Okay, so what are we doing here? Let's take a sphere, and the magnetization is uniform, let's say in the z direction, and I'm taking the z direction to be towards the right in the picture. So the magnetization vector is m in the z direction. That's all there is to it. And then we use the same idea, because you have uniform magnetization. There's not going to be, so we use this concept of the fictitious charges. It is negative divergence of m. Volume current density is going to be 0. You have a uniform, and so divergence of that is going to be 0. And you're then only going to get the surface current density, which is m dotted with n hat. And so it's sort of like you have these fictitious charges that are sitting there. Okay, and then we can determine that this is our z direction, or an equivalent picture of this is, I'm going to try to draw another sphere here. And what happens here is you get a sort of slightly non-uniform current density. I should use a different color for this. So you get current density on the surface. So surface current density, we know clearly in this case there won't be any, because the magnetization is uniform. There won't be any volume current density. It's only the surface current density. And so these two pictures are sort of equivalent. What this is analogous. Let me see. This picture is similar to the dielectric case, or a uniformly polarized sphere case, right? So polarization. And this is now, of course, the correct magnetic scenario, where you have the magnetization is produced by the surface currents, Km, and then you can calculate the Km as m crossed with n hat, right? So m dotted with n hat, that's your fictitious surface charge, versus this. Both of them should give you exactly the same sort of answer, right? And so that's what we're going to take a look at now. So let's use sigma star to give us psi m, the scalar potential, right? And we can use that to find the magnetic field, right? So by looking at this symmetry, you could see just by looking at the diagram, if the psi m is going to be psi m, it's going to be a function of r and theta alone. There is no azimuthal dependence, right? Because of the z direction, everything is just going to go around. So you have the azimuthal symmetry. And so the potential inside and outside need to follow a matching condition. So let's take a look at the matching condition. And the matching condition, of course, is a continuity of psi inside and outside. But more important one is because since you have a surface charge density, the normal vector of inside along the z direction, I should just, okay, that's fine. Minus psi out with respect to r on the surface, right? R equal to r. So you take the inside component, take its normal derivative, outside component, take its normal derivative, and normal is to the sphere is along the r direction, and r equal to r, and that should match with the charge density that you have, which in this case is fictitious. So you write down the corresponding magnetic terms. So m cosine theta. Okay, and similar to the azimuthal expansions that we did, you may remember for the inside of the medium and outside of the medium using the spherical harmonics, the expansions essentially try to follow the symmetry of your charge distribution. And so charge distribution here is following the cosine theta symmetry. So the inside field is going to be only AR cosine theta, right? So R dependence only first power, and then this is what picks out the that's basically P1 of cosine theta that picks out the symmetry of the charge distribution, and the outside is going to be B over cosine theta R squared. So these two, we combine the two at R equal to R, and that's going to give us. So these are now, these are essentially the expansion terms, only the surviving expansion terms. From inside multiple expansion, and this is surviving terms. I should actually write it down. From outside multiple expansion. Okay, so that's that. So we can then write down, you can write down R cosine theta as Z, and so psi m R theta would be 1/3. That's just the expansion, that's the coefficient. That turns out to be the value of A when you equate the two and then you satisfy the matching conditions. So that's for R inside, and then for R outside, you get similarly 1/3 m capital R cubed cosine theta over R squared. Okay, so this is, of course, I skipped a couple of steps, but this is straightforward. You can quickly do that. So you get that. Once you have that, then you can calculate this auxiliary field H, which is given by, give me just a second. The auxiliary field HM of R is similar to how electric field is negative gradient of the scalar potential. Here you get the auxiliary field HM, not the BM directly and the Bm can be determined using mu0, the magnetization of R, plus Hm of R is the magnetic field, right? So it's kind of weird compared to the electrostatic case. Uh, there you just add the external electric field plus the response of the material, which is polarization, and that gives you the total electric field. Here, you add the magnetization, which is the response of the material, with the magnetic field produced by the material itself to give you the external field, right? So it's just, a weird sign arrangement, if you will. But those are the two relations that are important in the situation where you can use the magnetic scalar potential concept. And then we can calculate the HM, and from that we can calculate the corresponding B. So all you have to do is take the gradient, and so when you take the gradient, HM of R is going to be, again, it will have two terms, inside and outside. It's a negative gradient, so minus 1/3 of M. That's all that's going to be. And the other calculation is slightly involved. When you take the gradient of cosine theta over R squared, you have to do it in the 3D spherical coordinate, or convert it into the Cartesian coordinates and then do it, and this is what you're going to get. This is similar to the dipole field, because of the mathematical similarities between the two. Okay, so that's that. And then the magnetic field is going to be 2/3 of mu0 m inside, right? So you just have to add mu0 m to the previous term, and then you get that. And E would be mu0 hm of R outside. So outside, nothing interesting happens, right? The magnetization is 0 outside, and so only thing that's left with mu0 hm. Okay, that's all there is to it. Everybody with me? Sort of, you understand the analogy with the electric and magnetic case that we can use to handle these sorts of things. So since we introduced sort of through an example, this auxiliary field HM, I should give you the matching conditions for it also, right? And connect it with the free current density and so on. So let's actually write that down. So just some theory on the total magnetic field. It will take us maybe a couple of minutes to do that. Then we will be done with chapter 13, right? So the curl of B, as you know, is mu0, the current density. The current density can be now split into two parts. You already know if there is magnetization, that creates its own magnetic current density. And then you have this free current density, that's what creates the external field, right? And so you get now mu0, the magnetization current density comes from curl of M plus the free current density. Okay, so nothing new there. We're just collecting all the thoughts that we had and some of the concepts that we developed to deal with the magnetized material. And so then you can write B of R as mu0 H of R plus M of R. So just like in the case of electrostatic situations, when you have a dielectric material present in the in some external electric field, the free fields where it was the D field, here the free field is the H field, meaning the free charges or free currents that are generating these fields. And so the divergence of B, of course, is 0. There are no sources, so you know that the curl of H is another vector equation that we need, kind of analogous to magnetic or the Maxwell's equations. But for the H field now, that is going to be now the source term for H is the current density, the free current density. And divergence of H is negative divergence of M, because only in that case are you going to get divergence of B equal to 0. And so they are opposite to each other, and you can write them through this fictitious charge density. And then you can even write down formally how H of R would look like, because you know it only depends on the free current density. So you can write down it as JF as a function of R prime crossed with R minus R prime over the inverse square term minus the surface terms, right? So that's the gradient of psi m. Okay, so that's how that kind of looks formally. That doesn't mean it's always easy to solve for, which we will deal with later in the next class. The differential equation methods to circumvent these integrals. Instead of using integrals, we are going to do the differential equation, partial differential equation solution techniques for determining these fields. So looking at the matching conditions, we have, let's say, two regions in which you have H, because you can see H is essentially governed by JF. The matching condition is that the parallel components of H are going to be discontinuous, and the perpendicular component would be the same, right? So the parallel component would be, you obtain that by taking a cross product with the normal vector, and that's going to be dependent on the surface current densities, right? So that's the KF, the free current density, and the parallel component are going to be with the dot product. H1 minus H2 is going to be M2 minus M1 dotted with N hat. So they're essentially going to be related with how the magnetization changes from region 1 to region 2. Parallel component of the magnetic field, which is our B field, that is always continuous. That's why you get the N2 dotted with B1 minus B2 is 0.
So B1 minus B1 or B1 minus B2?
Okay, so that's that. That completes the matching conditions, and matching conditions then allow you to determine fields when you have boundaries in space where the material properties change from one to the other.
Dr. Kapale?
Any questions anybody has?